Thank you very much. So before I start my last lecture, it's also my pleasure to thank the organizers for setting up this nice week, this nice school. So maybe we should give it up for them. Okay, so for my last lecture, I want to talk briefly about Kodaira dimension. So, well, X, let's say it's a surface, but the next definition it's much more general. And we have a line bundle. And the Kodaira dimension of L, it's defined by this formula. I'll write it and then I'll tell you some properties. It's hopefully going to become clearer what it is. But I think Simone already defined it. Okay. So maybe, yeah, properties. If the dimension of X is 2, then the Kodaira dimension of L takes values in this set. It can be minus infinity, 0, 1, or 2. And so when is the Kodaira dimension of a line bundle minus infinity? It's minus infinity if and only if all these dimensions are 0. So the line bundle has no sections, and none of its multiples has sections. Okay? And then it is 0 if and only if these dimensions are at most 1, and they are 1 at least once. Okay, and then let's look at, so now by Riemann-Roch theorem, the Kodaira dimension of L is 2 if and only if we consider, so let P plus n the Zariski decomposition of L, then P squared is positive. Okay? And then when is it 1? Well, it's 1 if we are not in any of these options. So P squared is 0. And for some n, we have at least 2 sections. And this is also the space of sections of the positive part. Okay, and then, so I gave you the definition of the numerical dimension. We can define the numerical dimension in general. For any L. And we have the inequality, so the Kodaira dimension of L is at most the numerical dimension. So an example which was already given by Simone, I think, we take X, an elliptic curve, and P and Q points in X, so that P minus Q is not torsion. And then, so okay, I'm realizing now that I gave you, so this definition is true in general, and then this property is just for surfaces. So I take L, the sheaf, the line bundle associated to P minus Q. So the numerical dimension of L is 0, and the Kodaira dimension of L is minus infinity. Okay, so this is the standard example where the inequality is strict. Okay, so another definition you probably already know. Kodaira dimension of X is the Kodaira dimension, oh, smooth maybe. Let's be. The Kodaira dimension of X is defined as the Kodaira dimension of its canonical bundle. And now for surface, for foliations. Now X surface. So if F is reduced, then we define the Kodaira dimension of F as the Kodaira dimension of its canonical bundle. And in general, we consider F tilde a reduced model given by the Seidenberg theorem. And the Kodaira dimension of F is defined as the Kodaira dimension of the canonical bundle of F tilde. Okay, so the proposition is that the Kodaira dimension defined in this way is a birational invariant. So, sketch of proof. As for the numerical dimension, it's enough to consider a birational morphism. So we have F tilde and F. And I told you that with the local form of reduced singularities, one can prove that the canonical of F tilde is the pullback of the canonical of F plus E, an effective mu exceptional divisor. And now we want to compare the global sections of KF tilde with the global sections of KF. And this is done by the projection formula. Okay, so these equalities with the projection formula. Okay, I could have done this for the numerical dimension, but I want to give you an example which shows that it's really important to look at a reduced model. So when it comes to looking at the birational invariance. So we're going to consider on P2 a pencil of conics. So I'm trying to reduce the computations as much as I can. So this pencil induces foliation F. And since F is not a pencil, of lines, well, its canonical will be OP2 of k with k non-negative. We don't even need to compute what it is. But then we consider the definition of the singularities of F. So what is a pencil of lines? Fix four. Sorry, what is a pencil of conics? We fix 4 points and then we take all the conics through the 4 points. And we resolve the singularities and we get, well, 4 exceptional curves. And then all the conics are separated. And this guy is a rational fibration. So X tilde, the blow up of P2 along 4 points. And F tilde is induced by F, a rational fibration. So Kf tilde is not Schütte effective. We did the computation right after the statement of Miyaoka's theorem, and therefore the Kodaira dimension of Kf tilde is minus infinity. Whereas this line bundle has positive Kodaira dimension. Okay. So this was the just a small example, and so yesterday I proved you by Macquillan, and a corollary of the proof was that if a foliation has numerical Kodaira dimension 0, then there exists some natural number n such that the nth power of Kf has sections. So if we translate this conclusion with the definition we just introduced, so this becomes, I don't know, well, maybe it's a little strange that a corollary becomes a theorem, but this becomes that numerical Kodaira dimension 0 implies Kodaira dimension 0. And actually also the vice versa is true. Okay, I won't prove the other implication. I would rather like to concentrate on the case of Kodaira dimension Okay, I forgot to mention that the idea of using the Kodaira dimension in order to study the geometry of foliations is due to Mendes and then McQuillan and Brunella. I'll write down some names later on. So the theorem here by Mendes and McQuillan is the following. So we consider F, well, let's say reduced on X with Kodaira dimension 1. So then we have a complete classification for F. F can be a non-isotrivial elliptic fibration, or it can be a Riccati foliation, or a turbulent foliation, or an isotrivial fibration into curves of genus at least 2. And we've seen this morning that non-isotrivial fibrations into fibers of genus at least 2 are not in this class. They are of general type, but we'll come to that. Okay, so how does the proof go? We consider the Zariski decomposition. Of Kf, and I'll state a claim. So there is a natural number such that the linear system of multiples of P induces a fibration F from X to C. And so this claim has nothing to do with foliations. It holds in general for a Neff divisor of Kodaira dimension 1. And I will assume the claim, and then we'll finish the proof. I'm not going to prove the claim. So, assuming the claim, we have our F, and F, capital F, a general fiber. And then let's look at the intersection of the canonical of F with the fiber. Okay, well, let's not forget that the general fiber is linearly equivalent to a multiple of P. So this is n P squared, and this is 0 because, where did I write it? because I told you that Kodaira dimension 1 was equivalent to p squared 0 and some other conditions. So p squared has to be 0. And this is n times p, and this is 0, because n and p are the positive and the negative part of the Zariski decomposition. So they are orthogonal. So this is 0. So, okay, now there are two possibilities. Again, either the fiber is F invariant or it's not. So, if the fiber is F invariant, then the foliation is the fibration F. And we compute our intersection product, which we know already to be 0, with the right adjunction formula. And okay, so now if F is a general fiber, this is 0. So it's contained in the smooth law. And then we get that the genus of F is 1. Okay? So why is the fibration now not isotrivial? We proved it yesterday. So yesterday we proved inside the theorem the implication in the other blackboard. We proved that if F is an isotrivial elliptic fibration, then P is numerically equivalent to 0. So F is not isotrivial. Okay. Okay, now the other possibility, if F is not F invariant, if F is not F invariant, then this intersection product is minus F squared plus the tangency order. And now F is a fiber of a fibration, so this is 0. So the fibration F and the foliation are transverse. And well, in this example, the first day, we have 3 options, of course. If the genus of F is 0, then F is called Riccati. If the genus of F is 1, then F is a turbulent foliation. And if the genus of F is at least 2, then X is, well, the singularization of F cross C tilde modulo a finite action. And the foliation is induced by the projection onto some quotient of F. Okay, let's see. That's the theorem. So what did we do so far? So we have F on a surface X. There is this Seidenberg theorem, which tells us that we can assume that F has reduced singularities. And we can find a relatively minimal model. And if F is relatively minimal, and Kf is pseudo-effective, we know the structure of N. So let's try to, now in these 4 days we've seen many of the possibilities. Let's try to see if we start. So we have a foliation on X, and we consider its canonical bundle. And we ask if it's pseudo-effective. So if it's not pseudo-effective, then we have this theorem by Miyaoka saying that F is a rational fibration. If it is pseudo-effective, then there are 3 options. Then the numerical dimension of F is either 0 or 1 or 2. And if the numerical dimension is 0, then by this theorem by McQuillan, the Kodaira dimension of F is 0, and F is generated by a global vector bundle. Modulo finite covering. Yes?
Vector field.
Thanks. Thanks. Modulo finite covering. Okay. If the Kodaira dimension if the numerical Kodaira dimension is 2, then this is equivalent to the Kodaira dimension of f being 2. And these foliations are called of general type. And they are called of general type, well, first of all, by analogy with surfaces, and then because they are very many. And we've seen it also, I think, this morning, in a sense, because if we have X surface and A ample, so we consider foliations with canonical bundle a power of A. And if A is big enough, this space is really big. So we get already a countable family of vector space of non-zero vector spaces. So this gives you at least a small idea why these foliations are a lot. And I am already fixing the surface. OK, so in numerical dimension 1, we have two options. The Kodaira dimension can be, it cannot be 0, because then the numerical dimension is 0. It cannot be 2, because then the numerical Kodaira dimension is 2. Then it can be 1 or minus infinity. And we just proved that if the Kodaira dimension is 1, then we have a classification by Mendes and McQuillan. Well, the question which was asked yesterday is there something here? So maybe I should add to all these results also the name of Brunella, who classified the smooth case. OK, so example. We consider delta the unit disk. And so delta cross delta, there are two natural foliations given by the two projections. So we just fix one. And so here the leaves are unit disks. So on the leaves, there is the Poincare metric introduced by Simone, for instance. So these metrics on the disks in family induce a metric on the canonical bundle of H. And now we choose a subgroup, the automorphisms of the product, delta cross delta, well, with a bunch of hypotheses. I'm forgetting something. But so all these hypotheses serve the irreducible. All these hypotheses serve the purpose of having the quotient compact. We consider, but no, of course it's singular, so we consider the singularization of it. And we can choose a gamma such that some other properties are satisfied. For instance, that the Kodaira dimension of Kx is 2, so X is of general type. And the image of the leaves, the foliation H on delta cross delta, are not algebraic in X. So we have ask that the image of L in X is not algebraic. So the foliation H induces a foliation F on X. And Kf has a metric induced by the one on Kh. And now this metric is not it's not positive in the sense you've seen in Simone's lecture. It's positive just in the direction of the leaves. In the other direction, it's 0. So this is not a very precise argument, but with a bit of work, you can prove that with this metric argument that the numerical Kodaira dimension of F, well, of F is 1. So now what is our foliation? Can it be of Kodaira dimension 1? So in all the results of the classification, we can see here all the varieties involved in these first three cases have Kodaira dimension at most 1. Okay, so let's assume that the Kodaira dimension is 1. Then since our variety is of general type, then we are in case 4. But in case 4, the leaves are algebraic. So we are not in case 4 either. So the only possibility is that the Kodaira dimension of F is minus infinity. this is a contradiction. Okay, so there is something indeed in that. Say it again.
Why is it that Kodaira dimension of x is possible in case 4? Wasn't it vibration on the curve?
In case 4, we could. Well, it's not. You're right. It's not necessary. Let me fill these. Okay, let me just finish because I have to lift the blackboard. So in that case, Kodaira dimension 1 and Kodaira dimension minus infinity, but numerical dimension 1. It was proved by equivalence, but then I think also by Touze in any dimension, that this is the only possibility, basically. It's okay. Okay, so we don't know. Okay, partially. The Touze's result has something to do with this case. Yeah. Thank you. Sorry. So, okay, is it clear that in 1, 2, 3 the Kodaira dimension is at most 1?
Kodaira dimension
of X. Of the ambient variety. So non-elliptic fibrations are supported on varieties of Kodaira dimension 1. Riccati foliation, the variety is ruled. In turbulent foliations, the variety has to have an elliptic fibration. So we have 1, minus infinity, 1. Well, at most 1, minus infinity, and at most 1. Okay? So yeah, here I am assuming you know a little bit about surface classification. And here you could have, I think, maybe you could have every possibility for the Kodaira dimension of X. But in particular, if you consider X the product of 2 general type curves, of 2 curves of genus at least 2, this has Kodaira dimension 2. Right? Okay. So, yes?
You said that gamma needs to be chosen such that the X is of general type. It's not always the case.
No, it seems to me that I read somewhere that you can even get rational.
You are uniformized by this X.
I'm not absolutely sure about that.
Yeah, but the point is that there are cases where you also compactify. You take something which is not co-complex, but I think when it's co-complex.
Okay. Okay, even better than. So gamma is.
This kind of Chaparovich type argument where you produce a lot of section knowing.
No, the quotient. What I'm saying that in the case to prove
That it's of general type. You reduce this section on the focus.
if the quotient you can find a finite index subgroup such that by Selberg lemma such that the quotient will be non-singular and it will be a quasi-type open from the singular case, and I guess that this would imply that the upstairs is clearly of general type and then downstairs will also be of general type. Quasi-type quotient of something of general type.
What is the numerical dimension in the theorem of equivalence?
Say it again.
What is the numerical dimension of the foliation? In this case, classification for Kodaira dimension 1 or foliation?
It's in this product of the 2 disks, you mean?
Or in these 4 cases?
Well, sorry, maybe my diagram is not very good, but so with the diagram I wanted to say that if the numerical dimension is 0, then equivalently the Kodaira dimension is 0. If the numerical dimension is 1, then the Kodaira dimension is either 1 or minus infinity, so it's 1. And if the numerical dimension is 2, then the only possibility is Kodaira dimension 2. No, thanks. Okay, so the only thing I want to discuss is, well, abundance for KF. So there are different formulations for abundance for the canonical of a surface. The first one, so any line bundle is said to be abundant if it reaches the equality in the inequality I wrote at the beginning. And we've seen that this is not satisfied for by the canonical bundles of a foliation. And there is the other famous formulation of abundance for, let's say, Kx. So this is a conjecture, well, this is a theorem in dimension at most 3, and a conjecture in general dimension. And goes as follows. If Kx is nef, then it is semi-ample. And then one could ask the same thing about Kf. So for Kf, we can replace the nef hypothesis with the by considering just P, and we can ask if P nef implies P semi-ample, and this is not true. I think a variation of the example I just erased gives a counterexample. So I won't give you a true example, but I write it like this. So there are examples of f on x of Kodaira dimension 2. So P is big, is a big divisor, and so a big divisor is an ample divisor on a Zariski open set, and we can describe the set where P is not big. So let's say the union of the curves such that P has 0 intersection with C. So this was described by McQuillan. This can be, again, chains of rational curves with 2 singular points at the two extremes, and then there are another tree of rational curves. Example, it's not any tree, but it's a tree satisfying specific hypothesis and a specific configuration of the points. And then there is a further example, which is cycles of rational curves. So these are rational curves. and those are rational curves as well. And so the first remark is that those have to be disjoint from the support of the negative part, and the restriction. Let me call this E. The restriction of P to E is not a torsion divisor. So P cannot be semi-ample. And I think I'm going to stop here.